All right, guys, let's go ahead and get started. I've got midterm corrections up here if you want to pick yours up. Your grade on Blackboard should be up to date. And I have some news for students here. The final exam is going to be on Wednesday, May the 11th. It was originally, I was told I needed to do it in person from 12 to 2. But I asked around, and it turns out it's mostly up to me how the exam is administered. So the current plan of action is I'm actually going to offer it online through Blackboard. I need to figure out how that's going to work. But my current plan is I will make it available on Wednesday the 11th from 8 a.m. to 8 p.m. So that whole day, you can take it at any time you want. But when you start taking it, you will only have 2 hours to finish. So it's still a 2-hour exam. It is still meant to be, closed internet, I would say. Like you're not supposed to go out and like Google stuff or whatever, but you can use your notes. You can use whatever you have on your computer. And yeah, hopefully I can make it work that way. I haven't really looked into it, but that's the current. So if you need to fly back home earlier than Wednesday, and this was your only final keeping you from doing that, you can do that. You can take this anywhere. How's that sound? Would people prefer, like I can also try to offer like in person as well. So like, if you're like, I actually don't want to do it online, I want to come in and write it down. I mean, we can give it out in person and then you do it during that time. Yeah. Can I make what? Oh, yeah, that's what I was asking. So we're definitely going to have it online. And I was saying, do I also need to make a paper copy? Like, is there anyone that would be like, yeah, I want to come in on Wednesday, like 12 to 2 and like do it in the classroom? Maybe, yeah, okay. All right, if you do want to do that, email me and then I'll try to make a paper copy for you if you prefer that. Yeah. Otherwise, just plan to do it that Wednesday. So it's only going to be open for 12 hours. So you have to do it that day. But yeah. Welcome, Chi. Okay, other updates. So there's 2 surveys that I'm trying to get you guys to fill out. Each one is 1% bonus for the class if we can get above certain thresholds. Okay. Yeah. This is where we are so far. So for the Meta EIR survey, last I checked with Chi, because she's the one that manages it, she told me that we have 35 responses. So that one, we're at 56% as of yesterday. So if you haven't submitted it yet, just fill it out, submit it. For the course evaluation on Blackboard, we're doing very poorly. So I don't know, is it longer? Is that one longer or just? Okay. This is where we are. So we are not at the 1% yet, but I feel like, you guys could get there. You can get there. For context, we were when we did the mid survey for the Meta one, we were at 83. So we just need like an extra 3 people, I think, 3-4 people to fill it out. And we'll be at 90%. On other news, you guys should have submitted homework 9 yesterday. Okay. I just released homework 10. There is no coding on this one, and it's much shorter, but it is released now. It's due in a week. Okay, cool. All right. Any other news or announcements from the class? Does anybody want to share anything with us? Jonathan? Graduate school application. That's awesome. Now you have to let the class know when you get in and where you're going, because now you've told us you're applying. So yeah. Okay, cool. All right, well, that's great. Grad school is cool, I think. Doesn't pay you money, but it's cool. I think so. I did a master's, right? So I do like grad school. I think I would have wanted to do a PhD if I was not tempted away by the money given to people. Anyway, so anyway, let's start class. So 285 for lecture 34. We only have, I think, 5 or 6, maybe 4 lectures left, right? 38. Yeah, so we're getting close to the end. Today, we got some chat messages. Oh, congrats. Telling you congrats. There you go, Jonathan. All right. Okay, so from last lecture, we were talking about finding the maximum flow in a graph. So again, this is, think back to your Vladimir, like your Putin days, where you're trying to send as many resources from from your home country to somewhere else. And we actually discussed one of these algorithms. It is called the Ford-Fulkerson algorithm. So this is the pseudocode at a very high level of how the algorithm works. Step 1 is you start with a flow that's 0 everywhere. So you are not pushing any material, right? You are just, there's nothing being moved. You have 0 flow. Then what you do is you construct a residual graph, right? So this is the graph where every edge has a capacity. And if there's already flow going along that edge, then the capacity is reduced by the amount of stuff you're already pushing, right? And in addition to that, that graph also has a backwards edge that lets you undo resources that you're currently pushing along that route, okay? So once you construct that graph, then you say, let me try to find a path from S to T in that graph. If a path exists, then that means I can push more stuff from S to T. So I calculate what is the maximum amount of stuff I can push along this path. And then I update my flow to reflect those new values. Where if I have a normal edge going forward, I just increase the amount of flow that I'm pushing along that edge. If I have a backwards edge, then I actually need to decrease the amount of flow along the forward version of the edge, okay? So we're gonna walk through an example. Maybe it'll make it more clear. So here's the graph we started with. So this is just a graph. You have capacities on your edges. So these are just weights on your edges. And the very first thing you do is you start by setting every flow. Every edge has an associated flow with it, like how much amount is going through the edge. You would initialize all of those to be 0. Any suggestions on how you might store this in implementation wise? Like how would you guys want to store the flows? What data structure might you use? Or you could use an array, yes. What does that require? So you need a way to go, you need a way to label the edges from 0 to m, right? m minus 1. So you need to have a canonical way of knowing like this edge is edge 0. So each edge, you probably need to then attach like its index to it or something. What's another way where you might not need to like enumerate the edges? Another data structure that helps you like map stuff from one thing to another. Yeah, you can use a hash map, an unordered map in C++. You can have your values be tuples, which are going to be, because every edge is defined by your vertices. So let's say your vertices are numbered, right? And then you can have that map to a flow. So there's many different ways to do this. We're not going to discuss in detail how to do it, but you would set all of those to 0. That's where you start. Then the next step in the algorithm says, create the residual graph. So the residual graph is a graph that does not have the capacities anymore. It's a copy of the original graph, but it just has edge weights. So it's just a normal graph with edge weights. This graph looks exactly like this one. Why? Yeah. Yeah, it's because we don't have any flow going through. So every edge is still going to have the same capacity because there's no flow, there's no capacity we've used up. And there's no backwards edges because we're not pushing anything. So the graph is actually essentially a copy of what you started with. And then the next step says, okay, find a path from S to T. So what would you guys, like, how would you find a path from S to T? Given a graph and S as the starting, like I tell you which vertex is the starting point, what algorithm would you use to find a path from S to T? Yeah, BFS, DFS, Dijkstra, if you want to, any algorithm that can tell you whether S is connected to T. So in general, the path you pick does not matter. The algorithm is like this Ford Fulkerson algorithm is going to work. It is correct no matter what path you pick. Okay. There are a few strategies that are smart so that you can have a good running time. And we'll talk about them in a bit. But for example, in this example, we ended up picking this path where we go from S up to this node, down to this node, and then to T. And then what we do is we calculate, well, how much flow can I push along that path? So what's the answer for this one? What is the maximum amount of stuff that I can push along the path I just discovered? Yeah. 4. Yeah, it's 4. And how did you guys find that out? Smallest number along the path, right? So if you're thinking about how would I code this, you need to first find the path using DFS, right? Then once you know the path, you iterate over the path again, and you say, let me find the minimum capacity, right? What's the running time of doing that? Does it make it worse than DFS? So DFS is linear. It's going to be O of n plus m. Does finding the minimum make it worse? It's still linear because you can just iterate over the path and you can find the smallest, right? So when you're designing algorithms, it is useful to think about that, because if it's not making it worse, then you can do it. It's basically free for you to do it, right? Cool. So we found the path. And then what we do is once we have the path and we know the flow, we update, we go back to our original graph and we say, well, I'm going to push 4 units here, 4 units here, 4 units here. So now we've increased our flow. Our flow is of size 4. And what we do then is we say, what is the corresponding residual graph for this new graph plus flow? And that's actually this one. So what's the main difference from what we had before? How did we construct this graph? And what would be the running time of constructing the residual graph? Anyone on Zoom? Anyone? No? Yeah, Isaiah? Huh? Yeah, how did we construct it? Yes. So you can imagine, let me make a copy of the original. Let me make a copy of this graph. So that's going to take O of n plus m time because I need to make a new one. So at minimum linear. Then I iterate over every single edge, right? For every edge, I'll keep the edge going forward as long as it still has space left, but I will change its capacity to be smaller. So that's an example of this one where we had an edge from here to here, which with capacity 6. But because we're pushing 4 flow, we now have an edge from here to here going forward. It's a forward edge with capacity 2. And in addition to that, if I'm pushing any flow, I will also create a backwards edge. So I need to label the edges. So I need to keep around that information that has a capacity equal to the flow that I'm currently pushing. Okay. This is called a residual graph. The idea is that you might want to undo, you might not want to push 4 flow through this edge. You might want to undo it. So that's why you add the backwards edge. And then you repeat. So we find a path. So this is what the graph looks like. And you'll notice that these edges, I drop them because the capacity is 0, which means you can't push anything through them, right? So now you repeat, you do the same thing. Is there a path from S to T in this graph? Yes. Cool. There is. Again, it doesn't matter which one you pick, but let's say we pick this bottom one. So it's actually 6, 10, 4. How much flow can I push through it? 4. So I'm going to go back and I'm going to update all of my flows to have 4 now, right? And then after I update all of the flows, I can construct a new residual graph, right? And again, all of this is taking linear time. So each time I do it, I have to, I copy the graph, I make a new one, right? It is not possible to do better than that. Just so you guys know, in the worst case, you will just always copy the whole graph. And you'll notice here that this edge disappeared because we maxed it out. So there's no edge going forward. But here we still have two edges. We have one going forward with capacity 6 instead of 10, and then one going backward with capacity 4. And then here we have one going forward with capacity 2, and then one going backwards with capacity 4. Right? Now, oh, my phone is ringing. Oh, okay, that's fine. Okay, ignore that arrow that I put in. Is there a path from S to T in this graph? Yes, there is. So I pick a path. Maybe it's the only one, but maybe there is. So this is one path. I can go from here to here, from here to here. I can take this backwards edge back up here, and then I go forward to T. How much flow can I push along this path? 2. Okay, so maybe it's covering you guys. This is the original graph, and I said, well, there's actually a path from here to here to here, and then going backwards on this edge. Okay, so this is the first time we actually see a backwards edge. So that's why I have this arrow here. What does that mean for this 4? So for these edges, we know what to do. I'm just going to increase the flow. I'm going to say the flow is 2. The flow is 2. But for this edge, what I'm actually going to do is I'm going to decrease the flow by 2 because I'm going along a backwards edge. So in a way, our first path that we picked, it was not optimal to push all of the flow through here. Okay, so we're actually pushing some stuff back. Yeah, so we remove flow from that edge. Everything else is the same as before. So now this is what your flow looks like. Now, I do want you guys to notice as well that every time we do this operation, our flow is increasing, right? Because we're always able to push more and more, like at least one more, right? So now we're at flow 10, okay? Any questions on this so far? This is how the algorithm works, okay? This is what your graph looks like now if you do a residual graph. So it's the same process where for this edge, I have flow 2, capacity 2. So there is no forward edge because I filled it up. But I do have a backwards edge with capacity 2 to maybe undo the flow, maybe undo it. And then I repeated that for every other edge on the path. Okay. Is there a path from S to T? Did I? Yeah, I missed an edge. Or, huh? Yeah, well, so there is, yeah, so there's also an edge going from here to here because this edge has capacity 3. So there's the backwards edge for the 2, and then there should be a forwards edge also for the 1. So I think I've probably missed it. Yeah. Yeah, you can go down, back up, this way, this way, this way, this way. Okay. So I think the main thing is I have this edge is like, so there is a 1 here, so I had it, but I think I missed putting in the other one. Okay. Oh, yeah, that might be it too. Oh yeah, because there's two orange here. Yeah. Okay, but it turns out there is a path, and you guys can double check me. how much can I push along this path? 1. So I go ahead and do that. I push 1. So that means for every forward edge, I'm going to increase the flow by 1. For every backwards edge, of which there's this one, and this is the only one, I'm going to decrease the flow by 1. Okay. So now my flow is going to look like this. Okay. So in our very first path, we actually had this flow at 3. But it turns out we've been decreasing it by 1 a couple of times. Now, this is what my residual graph looks like now. There should be an edge from here to here with capacity 5. Just, I mean, you can look at this and say like this has 6 and only flow 1. So you can figure out what the 2 edges should be, right? Is there a path from S to T in this graph? There's not. So we're done. We have nothing left to do. There's no path. And one way to look at that is there's a cut here that separates S from T. And along this cut, there are no edges going from S to T. Okay. It also turns out that this is the minimum cut, this specific one I picked, because the value of the minimum cut is 4, 3, 4. So it's 11. And the value of the maximum flow is also 11. Okay. So in conclusion, the algorithm works. Okay. We're not going to spend too much time proving why it works. But the idea is that if you cannot find a path in the augmenting graph, GF, then F is a maximum flow. So our goal was to find the maximum flow. The way the algorithm works is it tries to find some flow from S to T. Once it has some flow, it creates a new graph that reduces capacities if you're pushing stuff through those edges already, but also adds edges going backwards in case you want to undo some amount of flow. And the idea is when you can no longer find a path from S to T, then you have found the maximum possible flow. Okay. Here's the argument for it. So again, suppose there is not a path from S to T in GF. So we got to the point where we can no longer find a path. Then there's going to be a cut. There are going to be vertices that you can reach from S. And there are going to be vertices you cannot reach from S. That's what it means for there to not be a path from S to T. In particular, T, at minimum, T is going to be here, right? So you can define a cut. And here's an example graph where there will exist some cut that includes T on one side, and then all the vertices you can reach from S on the other side. And the reason why then this must be the maximum flow is that any flow that exists would have to cross this cut, okay? But it cannot because we have saturated all of the edges along that cut. Because we can no longer find a path, we only have backwards edges, which means we fully filled up the edges along that cut, which means the flow has to be the maximum flow. Because any flow has to cross that cut. Does that make sense? Maybe? Sort of, a little bit? Okay. The other thing, yeah, so the value of this cut, this is what I was saying. So the value of our flow, whatever flow this has to be equal to the cost of the cut. Okay. But the cost of this cut, because it's a cut, has to be bigger than or equal to the minimum cut. Because by definition, the minimum cut is consider all possible cuts, take the smallest one, right? By the lemma from last lecture, the cost of the minimum cut is greater than or equal to the maximum flow. So this value, this flow that we found has to be greater than or equal to the maximum flow. But by definition, the maximum flow is the maximum. So this flow must be the maximum, right? It cannot be bigger. It has to be equal, right? Therefore, F is the max flow. Therefore, when this algorithm stops, you have found the maximum flow. There is no flow that is bigger. Okay. That is the sketch of the proof for why this works. But you guys should take some time to work through some examples or like look at the slides again and think about it. Okay. It is not immediately obvious that this algorithm should work, right? We're basically just saying, try to push as much stuff as you can, and then try to find some other path, push more stuff. Okay. Okay. This also concludes. So there is some more general. This is like a mathematical theorem that's called the min-cut max flow theorem. Last time we had an argument as to why the minimum cut was bigger than or equal to the maximum flow, right? Because any flow has to cross a cut. Therefore, the minimum cut has to be at least as big as the maximum flow. Right now, we just showed that our flow has to be bigger than or equal to the minimum cut. So if you reason that out, it means that they have to be equal to each other. Because A is bigger than or equal to B, and B is bigger than or equal to A. So they must be equal. There is no distinction. And that is actually what the min-cut max flow theorem says. It says the value of the minimum cut is equal to the value of the maximum flow. And historically, this is kind of interesting. Oh, I guess I skipped that slide. Oh, no, I did not. This is interesting because if you think about it, the US was trying to figure out what is the minimum number of railways I need to destroy to cut off the resources. But the USSR is trying to figure out what is the maximum amount of stuff I can push through my network. And it turns out the answer to both of them is the same. So they were working on the same problem. Okay. Cool. So if we talk about how long this algorithm takes, so the algorithm always works. You can pick a path however you want. It will work, okay? But there are better ways to pick paths than others. So for example, in this graph, so here's our example graph. Suppose that C is like a really big number. So we have these capacities are really, really big, but this capacity is 1. What is a really bad path to pick? I'm trying to push stuff through it. What's a bad path that would like not help me get to the maximum flow quickly? What is the maximum flow, first of all? This is a very simple graph. You guys should be able to look at it. What is the close? You need a, yeah. It's 2C because you have C going this way, C going this way. So that 2C is the maximum flow. Yeah. Yes, right. So you can imagine, like I told you, the algorithm will still work. If you can pick any path, it'll still work. It'll eventually get to an answer. But there's a bad path here, which is like if you pick the middle one, you will increase your flow by 1, right? Okay, so if you pick this middle one, your flow increases by 1, and you're like, now you ask, is there a path? And you can again pick a bad path. What's the bad path in this graph? Yeah, it's the path that goes back through the middle. Okay, so this path, you will increase your flow. So every time you pick a path, it does increase the flow. So you do make progress, but you'll increase it. You'll undo the flow here, and then you'll increase these flows by 1, right? So how long would this take if I'm always picking, like, let's say I keep going back and forth between those paths. How many times does my algorithm run before it's finished? Or how many steps does it take? Yeah. Yeah, so we know the maximum flow is 2C. And each time we do one step of this, we increase the flow by 1. We know that once we get to the maximum flow, the algorithm is going to end because it's not going to find a path. So it'll do that 2C times, right? And each time I do it, I have to run the whole, like, create a new graph, find the residual network, find a path, right? So each time I do n plus m work, and I do it C times, So it's big O of C times NM. Okay. Which if you know your network has not very large capacities, that's not that bad, right? Like if your capacity is at most 10 for any one edge, if your max flow is at most 10, then it's not that bad. But yeah, I'll go on for C steps. So here's a couple of stuff. Here are better ways to pick your paths to avoid this problem. There's actually two well-known versions. The proof is in the lecture notes, but we're going to skip it in lecture. You're not responsible for it. There is an algorithm that says pick the path that is the shortest distance according to BFS. So pick the path that uses the least edges. That algorithm is known as Edmondson's CART algorithm. Its running time is NM squared. So essentially it repeats at most N times, or sorry, at most M times. That's not the only way to do it. Let me see. Okay, I didn't put it in the lecture notes. There's another way that is called pick the fattest path, which is out of all the possible paths, pick the one that has the biggest minimum edge weight. So the one where you can push the most stuff through, that's the path you will first push stuff through it. That also has a similar running time. It's in the lecture notes, but you guys are not responsible for it. Cool. Okay, there's more. So for the rest of lecture today, so this algorithm is like both really applicable because I told you guys like the USSR, like the reason it was invented was because somebody was trying to solve a real world problem. But it is also very useful in other ways that are not just let me try to push stuff through a graph. Like let me try to move resources. So we're going to talk about a few examples where it might be useful. One of them is called maximum bipartite matching. That is the name of the problem. This is actually a very common real world problem, but this is what it's called in CS theory land. The other one is integer assignment. And then the last one we're going to cover, if we have time, is something called deferred acceptance. Do you guys know any pre-med? Do you guys have like people that are going to be doctors in this school? Like people that are like pre-med? No, okay. So this might not be as interesting to you, but we'll talk about it anyway. Okay. So this is what is called the maximum matching in bipartite graphs. So again, we talked about bipartite graphs before. Do you guys remember what they are? Yeah, go ahead. Yes, they actually come up a lot because they are very natural sets of things that do not connect amongst themselves, but connect to each other. So students and swag creates a bipartite graph. If you say the edges are like this student wants this swag, because swag do not want each other. So there's not going to be any edges amongst the swag. And for the purposes of our problem, students do not want each other either. So there's not going to be edges between the students. So naturally, this one's a bipartite graph. A more common bipartite graph that you will see is, for example, users and posts at Facebook, users and groups. Yeah, users and whatever you can think of. Like on Pinterest, you have pins and boards, or users and boards. So all of those actually form bipartite graphs. Okay. So once you have a bipartite graph, one question you might ask yourself is, what is the maximum matching? So a matching, or well, let me finish this. So different students only want certain items. So this is the problem this is the example problem. And the problem is, how can I make as many students as happy as possible? Okay, that is the maximum matching. So a matching is just an assignment of like student C is going to get this t-shirt, but once he gets it, nobody else can get it, right? Because there's only one, he took it, right? Any assignment is a matching. The maximum matching problem is, how do I find the assignment that matches the most people? Okay, so how would you guys do this? Maybe for this graph even, what is the who gets what so that as many students are happy? You guys think about it. You don't have to answer it. Maybe if you figure out for this problem, you should start thinking, how would you do it for a problem that has all of the students at NCAT and all of the swag? So you've got like, how many students are here? 3,000? 1,000? Oh, 13,000? Oh, okay. So you can imagine you wouldn't want to do that yourself. Even looking at the graph, you'd be like, that's too hard. So you want to think of an algorithm that would help you. Okay. So hopefully you guys came to this conclusion. This is the maximum bipartite matching where student B is unhappy. This is the best you can get. You can only get 4 of the students to get what they want because the things they want just don't work out for student B. Okay. Now, there's a solution. So MaxFlow, so the algorithm we just talked about, can be used to solve this problem. How? You can take your original graph with edges. You can add a source node that connects to each of your students. You can add a sync node that connects to each of your swag. And then you can say every edge has capacity 1. And then you can ask the question, what is the maximum flow that I can push through this graph? It turns out that the maximum flow is equal to the size of the maximal matching. Why? Who can maybe like explain why that's the case? Yes. So I'm going to define a new problem where each edge has capacity 1. So I can at most push 1 unit through it. Another thing I didn't tell you guys about maximum flow, because of the way our algorithm works, if all the edges are integers, your answer is going to be an integer, right? Like there's no way to push like half a unit. Like the way our algorithm works never pushes half units. It's always like, let me find a path. I'll push as much as I can. If everything's an integer, then that's going to be an integer, right? So they're always integers, okay? But what I'm saying is that the maximum flow along this graph is actually going to be equal to the size of the maximum matching. It is still 4. The maximum flow is 4. Yeah.
So basically, the more matches you have, the more flow goes across from SG. So that's the connecting paths.
Yeah, exactly, because those are the connecting paths. So from this side of the graph to this side of the graph, if I make each edge have capacity 1, if I have a matching, I can take that edge and push 1 flow through it, right? So the maximum matching is going to be equal to the maximum flow because whichever one gives me the most matches, I can push, if I have 5 matches, I can push 5 units of flow through it. Cool. And that's exactly what happens. So these, I think, yeah, so these are the matches. So the edges that get flow going through them are actually equal to the match edges. Yeah. And the maximum flow is equal to the maximum match, which in this case is 1, 2, 3, 4, because only 4 edges can push flow through. Okay. No, the blue is representing the edges that do not carry any capacity. That we cannot push any flow through them anymore. Okay. So again, we talked about an algorithm to solve maximum flow, but that algorithm is also an algorithm to solve the maximum bipartite matching problem. Okay. Yeah.
So the last student still doesn't get what he wants?
Student B does not get what he wants. So student A is going to, because he has an edge that has flow going this way, he is going to get this shirt. This student is going to get this shirt. This student is going to get this one, and this student is going to get this one. And then that's it. Nobody gets the cup. And this guy gets nothing because I guess one way to think about it is there's too many people that want this shirt and there's just not enough shirts to go around. Okay. But I think the main thing I want to like drive to you guys is that, and this applies to a lot of algorithms we've learned, these are very general algorithms that you can try to use to solve many different problems. Okay. So again, so we go about why this works. So Serena gave us an idea of why this works. But the value of the flow is 4. Because the capacities are all integers, all of the flows are going to be integers, which means for each edge, the flow is either going to be 0 or 1. So for any edge where, and then the other thing that we know is that the stuff going into this node has to be equal to stuff going out. So the amount of flow going in has to equal the amount of flow going out. We still have time, right? Yeah. Okay. So that's why, like, it is important that we set the capacity of this edge to 1, because this edge is saying this person can pick at most one thing, right? Similarly, this edge here is saying this item can go to at most one person, right? So defining the capacities to be 1 matters. It turns out the capacities here don't actually matter, but you can set them to 1 if you want. As long as they're not 0, they don't actually matter. Cool. And then the edges with flow on them form a matching. Any matching gives a flow. And then the value of the flow is the size of the matching. Cool. So we conclude that the maximum flow corresponds to the maximum matching. So here's a slightly more complicated example called assignment. These are called assignment problems. So you have a set X of things, aka the students. You have a set Y of other things, aka tubs of ice cream. Okay. And what's going to happen is that each student can participate in some number of matches, aka student X can only eat 4 scoops of ice cream. He does not want more than 4 scoops of ice cream. And each Y can only participate in CY matches, aka this tub of ice cream only has 10 scoops in it. So I have many different flavors of ice cream. Each one has a different amount of scoops. I have many different students. Each one wants to eat at most a certain amount of different types of ice cream, right? Yeah. So the problem statement is, well, let's get into it. So we'll walk through this example, and I think that'll make it a little bit clearer for you. Here's an example. What this is saying is, for these flavors of ice cream, this is how many scoops we have, right? So we have 6 of chocolate, right? 3 of zesty lemon, right? That's the total amount of ice cream we've bought, okay? For these students, this is how many ice cream scoops they can have at most, right? So he can, like, this person's okay if they gain a little bit of weight. So they're like, I want to eat 10 ice creams. And this person is like, I really can't, I can only have 1 scoop, okay? So they have a maximum amount of like scoops I can eat. And in addition to that, they have a preference for which tubs of ice cream they want to eat. So this person can eat at most 1, but he's like, I would want either 1 chocolate or 1 vanilla. I'm happy with either of those, but I can only have 1. Okay. So this is like it's sort of like a made up example, but you can imagine that in the real world, this is basically trying to do resource allocation. So I have some items of something that I only have so many of that are of different types. And I have some people or some other things that need those items, right? I saw somebody roll their eyes. No, it was not related to this. I don't know. It's an interesting example. We should do it with pizza or something. What do you guys eat for fun? Not ice cream, right? Ice cream is kind of like, is ice cream? Ice cream is good, right? Which I should have done boba flavor, maybe. Okay. All right, so this is the problem. Your goal is to make as many students as happy as possible. How do you do it? Yeah.
Couldn't you start with taking like the egg that takes the least amount of cost for the ice cream? So like if we took a 10 and we decided to go with 10, well, only 6 scoops of this 10 ice cream, so that would work. So they would take the 5, but that was the wrong person to choose.
Yeah. Try to, so you're probably thinking of greedy algorithm-ish kind of thing. This is part of the reason why these problems are hard. Sometimes you don't know how to approach them. We are covering a maximum flow lecture. I will tell you, this still relates to maximum flow somehow. So how might you construct a graph where the maximum flow for that graph tells you who to give what ice cream? You wanna, yeah, Isaiah?
So I see like, so the person who wants 10 scoops.
Yeah.
The 10 is going to the one. So it's like, yeah, to the Ben and Jerry's one. So
Well, it's,
would he want Ben and Jerry's more than he wants Zesty Lemon? Is that what that's saying?
oh, that's a good question. That is not what it's saying. What it's saying is this person wants exactly 10 scoops of ice cream. Okay, or at most 10 scoops of ice cream. He can have at most 5 scoops of Zesty Lemon, and some 10 scoops of whatever, the Ben and Jerry's Cherry Garcia. So he can say, you know, I want 5 of, you know, I want 3. I guess, yeah, he can only, he might be like, I'll take 3 of Zesty Lemon, which actually runs out the Zesty Lemon. And then I'll also take, you know, 6 of the ice cream. So he gets both of these and he's really happy because now he's got 9 total, right? The goal is to maximize how happy everybody is. So everybody wants to get to their maximum, but you want to get everyone to be as close to the maximum as possible. So maybe it does not make sense to give him, you know, all 3 of the lemon. Maybe it's better to give this guy who only wants lemon, to give him the 2 of the lemon, right? So, yeah. But any ideas on converting this to maximum flow? Yeah, Jonathan? Yeah. Okay. Oh, I see. For this specific problem. Well, that's good, but I want the general. I want somebody to try to think of a general. So like, you know, if I had 100 students and like 300 different types of ice cream. Yeah, Serena, you wanna?
You put a source node connecting to the students, and the weight of the lines would be like the numbers there represent like the maximum amount that you take, right?
Yes. So this is like, I can take at most 4 scoops of ice cream in general, like 4 of anything. That is the most I can take. Yeah.
So that would be that capacity line to S. And then on the other side, the T would be connecting to all the ice cream flavors, and their capacity line would be those.
These are how many you have of them. Yep. And then what about in the middle? Do you do anything to these edges, or you keep them? You keep them? Yeah. All right. Lester? Yeah. Yeah. So the only thing you want to change in the middle is you want to make sure these edges are directed from S to T, right? Because right now they're just telling you like these people want this stuff. They're not telling you which direction, right? So that's exactly it. And once you convert, so you would convert that problem into this graph. You would say, I have a graph with a source T that connects to each of my nodes that correspond to students. Each connection is going to have the capacity equal to how much can that student, like how much does that student want to eat at most. All of these edges, I'll make them directed, right, from the S side to the T side. And the capacities are going to be equal to how many that student wants to eat of that ice cream. And then similarly on this side, I'll have edges from the ice cream to T, and the capacities will tell me how much of that ice cream I have. And then what you can do is you can say, well, now the maximum flow, the maximum amount of stuff I can push from S to T will actually tell me not only what is the maximum number of scoops of ice cream that I can, you know, give out and make everybody as happy as possible. It'll also tell me how many of each scoop of ice cream to give to which student, right? So for this problem, it actually turns out this is the maximum flow. And yeah, so this is the maximum flow. And yeah, so like this student, for example, only gets 1 scoop of vanilla ice cream, even though, oh, he can only have 1. So this guy wanted 10 scoops. he ended up getting 1 of zesty lemon and 6 of the Mali cherry. Okay. All right, so we are at time. There are more slides that we will continue to cover, but in general, there are a lot of examples of problems, usually resource constraints, that you can transform into a maximum flow problem. And now that you have an algorithm, like you guys haven't implemented it, but you know it is possible to solve the maximum flow problem, then all of these problems are solvable for you. Okay, cool. Great. All right, see you guys on Zoom, and have a great weekend.